So today we will continuously the last discussion regarding the devices physics to understand how the devices should be done. We must start to have a brief overview on quantum mechanics. Can you see me perfectly on the screen? I think it. I will start with a brief overview on quantum mechanics. Since the historic point of view and some formalities to describe the physics on quantum world. So why we must understand the quantum mechanics to build the devices in physics? We must understand because every interface that we construct, which means that we have some specific thank you. Specific features, and this interface will give some characters that could, for example, block or transport charge, and also can enhance the mobility, for example. So everything that is necessary to construct these devices, we must understand into atomic scale. And when we go into atomic scale, we have a difference on the physics. And this physics is not ruled by classical physics, but it's ruled by quantum mechanical laws. So the main reasons behind that you will see on the end of this course today is that bonding structure will be determined through quantum mechanics modeling, and everything that we do on devices physics is applying quantum mechanics on it. I think it's because of my animation here that it goes over there. I don't know. Maybe during the change the computer. I don't know why. But the quantum world, we can describe it. There is a linear condition when we go to the real world and go small scale. And when we go to small scale, we can see that those rules that we usually determined by classical mechanics is not simple rules in quantum point of view. So we must change some classical descriptions to new description that we call modern physics. And this modern physics will rule some particles and give some new particles that we can understand the matters and also understand how the light, for example, interacts with matters. That is the main reason that we must understand for materials and to build different devices. So in terms of physics, quantum mechanics, the energy is not more continuously, but it is discrete energy. So it means that we have some specific values of energy, and those specific values must be limited by some momentum or some position of particles that we are observing. So in this way, in terms of history, we could see around the 1900 year that physicists start to study the interaction of light with matter, and it would not behavior like the same as observed by large scale. And we have this breakthrough on the physical laws that when we go smaller, we have quantum mechanics. When we are in the scale that we can see by our own eyes, we describe it by classical mechanics. And when we go with particles moving in high speed, speed higher than, similar than light speed, we can describe it by relativity. So we have three different point of view of physics we can see on that. And we are focused on the quantum, so we must reduce the scale in order that we cannot see by our own eyes. We must use some experiments to see, for example, the atoms and the particles that are in the smaller scale. And when we go small scale, we are ruled and they use Planck constant. So everything that we do on quantum mechanics, we use the Planck constant that describe the quantization of quantizing physics in the quantum scale. So the first experiment that historically started the quantum mechanics was the photoelectric effect. The photoelectric effect is the interaction of light with matter. So we must understand how the light interact with the matter, and these electric effects are the correlation between emission electrons from the material and the light that we are incident on it. So depending of the characteristics or features of the light, we have different behavior of the electrons that are repelling from the matter. So in this way, the energy, for example, of the electrons will be ejected, for example, with the same energy in different light intensity or light color. So this was the first experiment that described the quantum world. And this phenomena was observed by Albert Einstein around the 1905 year. And this experiment described the quantization of light and the energy that is related with the light. And a brief overview on how the experiment was done is around here. You can see that we have some chamber. This chamber is under vacuum, and this vacuum, so it means that we don't have any atoms on the chamber, and we have one anode that is golden anode, for example, or another metal, and this anode will be interacting with the light that will be put on metal. And the chamber also was made of quartz because we do not interact with the light that is on the metal. So the chamber is connected with one source of an electrical source. So it means that we can polarize the anode and cathode. So it will guide, for example, the particles that will be repelled when the light interacts with the matter. And when we guide those particles, we can polarize somehow in the way that we can move the electrons that are negative through one's direction. And when we change the polarization, we can repel these particles because of the same polarizations, and it will decrease the velocity of the particles and further. So the experiment was seeing how the light interacts with those particles, with those materials, actually. And this interaction will give free particles, and we could, in that time, the experiment could be observed through amperemeter, and depending on the current that is released on the interaction of light with the metal, it is observed how the movement of the particles ejected from the metals could be related with the light that is incident on the metal. So if we change, for example, the intensity here, we will change the number of waves that you can see on the picture. And if we can change the color of the light, we will change the frequency of those waves. And this is correlated, seeing some relationship between the potential appliement, light, color, light intensity, and the correlationship with the intensity of current released on the amperemeter. So, for example, here, one observation was the relationship between photocurrent. What means photocurrent? That is a current where it can be observed when we incident the light. So without light, we don't have photocurrent. And the light can be managed the intensity. If we increase the intensity of the light, we could see large photocurrent. But when we polarize the potential of the different of potential between the anode and cathode, we can reach one thing that we called stopping potential. And even if we change the intensity of light, is the same stopping potential that is observed. So we could, this is not explained by classical mechanics, because it would be expected that changing on intensity would directly impact on changing on stop potential. And also that even that there is a change in the intensity of photocurrent, these changes doesn't mean that the photocurrent is changing the energy, just the number of quantities that is pulled on the materials. So, and when we changed the color of light, it directly affect on before I start to talk about the color of light, when we are talking about the stopping potential, you can imagine here with this picture. A reminder that the picture that we have the anode and the cathode, and if we switch the polarization of anode and cathode, we have a difference on the accelerating and the retarding of the movements of the particles that are released. So we could directly correlate this difference on energy applied through potential using this kinetic energy of particles that are repelled from the material. So we could correlate the energy, kinetic energy, with this retarding potential, because when we have the same amount of energy to block the movements of particles, we could stop the current that is observed in this graph. So here we can correlate the kinetic energy of the electron with this potential that is applied in the experiment. And this correlationship is with electron charge, that is the charge of one electron. So in terms of light intensity, as we discussed earlier, reducing the light intensity decreases the photocurrent, but does not change the stopping potential. So the intensity controls the number of electrons that are emitted from the material, and not the kinetic energy that when they release those materials. When we changed the frequency of the light, which means that we changed the color, for example, we investigate color blue, green, and red, and this frequency is correlated with those kinetic energy. We can see that there is some energy with color, a specific color, that would release this electron depending of material composition. So for example, if we change metal 1 for metal 2, this color would be different. For example, the metal 2 needs the color of light blue, and the metal 1 green to have the releasement of this particle. So this is also a breakthrough, because there was not any classical observation regarding the frequency of the light and the interaction with the energy that is the particle released. So the classical theory would predict that energy should be continuously, not with specific values. The kinetic energy would increase with the intensity, and this was not observed using the experiment. And there was somehow finite emission delay, and we did not observe it. And so this experiment could give a breakthrough on the classical, and it's not a direct breaking the Maxwell equations, but just how the energy is transmitted during the interaction, not during the propagation of the wave. So in this way, to continue the quantum world, we must change how we see the light. And this was the first proposition of Einstein, that we could change how we see the light to energy packets. So the light is not just a wave, but this wave behaves like packet of energy, and we call it as photons. So the photon has energy given by hv, h actually, where h is the Max Planck constant, is Planck constant, and the ni is the frequency of the wave that is associated with this, for example, the light. And the photon travels through the space with speed, constant speed c, that's speed of light. And through this definition, we could see in this specific feature that one photon interacts with directly one electron, but has some specific things that is different. But in general, one electron interacts with one photon, and one photon gives one's electron interaction. And the photon also has zero mass, and the photoelectric effect could be used, the energy of conservation and the relationship with those experiments using energy kinetic equal Ag ni minus phi. So Ag ni is the energy of the photon, and the phi, when the photon interacts with the matters, the phi gives the work function of those materials, and this work function is related with the potential barrier and the electronic binding energy, as well as some analyzed fluxes inside the material. So this phi means that there is some minimal energy that we could give to the material to release this electron. And if the light, when the light interacts with the matter and has the same value of the minimal energy of the surface, it will have no kinetic of electron that is repelled. So we must, to observe the electron, give some energy higher than the energy of surface. Okay, so this what I thought was regarding interaction of the light with one atom, for example. When we go to materials, we don't have just one specific atom, and we have some distribution regarding the interaction of the atoms with another atoms surrounding. And these interactions will give some lattice. And this lattice, as I talked on last class, will be organized in crystals or amorphous. And this also has some distribution of energy in the electrical states. So the photoelectrical electrons, that means when the photon interact with the matter, directly interact with Fermi C, not directly with one atom in specific, when we analyze it on experimental point of view. So this work function will be depend on crystal orientation here. If we have some orientation with some doping, for example, there is difference. And we have a surface termination, for example, different energy of different morphology for some interaction with another surrounding. And also, if you have some adsorbates or contamination, will be directly impact the energy of released electron. So these energy losses arises from electron photon scattering, or electron-electron interactions. The phonon, I'll just give a brief discussion on it, but we'll discuss more on the next classes. But it's the morphological reorganization of matter, and these different on geometry of the system can be released by energy, and this energy released is quantized as the electron-electron interactions. So the photoelectric effect can be described by time dependent perturbation. So here we have this transition through Fermi-Golden rule. So here we have this transition from initial state to final state, where we have the Hamiltonian of system and these auto aging vectors that describe the system, initial system and final system. And when we have transition between initial and final system, this rate can be predicted through the proportional square of the Hamiltonian system. And this is correlated to delta function. And this we can know how to go from one initial state here to final state in terms of energy, and here distance. So here, for example, one electron goes to interaction with the light. The electron absorbs this light and goes to final state here. This transaction can be predicted using this equation. And this is the basis of photoelectric effect, because of the we can know the rate of this transition using the knowing of the material morphology, for example, and how we could interact with how this matrix of morphology could interact with the light, so it can predict the energy states of the system. So this is the microscopic interaction Hamiltonian between the electron and radiation field. So in terms of electrical classical modeling, we don't break as I told you, the Maxwell equations, but we can we just describe it, the energy, the transport of energy by wave, And when the wave interacts with the matter, the energy that is given to the matter, it can be described by particle. So we have this called duality between the wave and particle behavior of light. So sometimes the light can be described by wave and sometimes can be described by particle. So the discrete energy comes of the particle, but the propagation of energy comes from the wave. So this also satisfies the Maxwell equation. So just remembering how the Maxwell equations go, we have electrical magnetic field describing the propagation of light into the space. And this electromagnetic field has wavelength, which is the distance between two same points in the space. And we have magnetic and electrical field perpendicular. And these fields of electric and magnetic are propagated in one direction and reflect in another direction. So this is one dimension propagation. And when we go to quantize of energy, we can describe this wavelength, these photons with some wavelength, and the wavelength that they will have some specific energy, and this energy will be ruled by the frequency of the wave that is associated with this light. So, for example, here is just was a bit small here, but if we go to increasing frequency, we have a higher frequency here, and this frequency in terms of energy is higher. So when we have gamma rays, is higher than X-rays, is higher than UV, and between UV and infrared rays, we have a visible light, infrared, microwave, and the lower amount of energy of light. So we can separate the energy of light into the spectrum. And this spectrum goes from the small energy and to the high energy, and is directly related to the frequency and invertedly related to the wavelength of this wave. In terms of devices physics, we usually find some materials that can be interacting with the visible light because of the device's rules, the energy necessary for those absorption of the light or emission of the light in the visible spectra. So usually the energy that we are focused on this spectra is around the visible light. We don't, for example, if we have some semiconductor here applied with invisible light, when we increase the energy or decrease the energy of the light that is hitting them, we can have this material isolated or semiconductor. So in terms of application, we must check which is the range of light that we are observing. Hello.
Yeah,
Bonjour.
we cannot find.
Sorry.
Sorry, and we work in the another class.
Okay. Oh, I'm
So sorry.
so sorry. Don't worry at all. I think that let me see here. So, thank you for coming, even that I just gave a brief overview on quantum mechanics and why we must understand the quantum world to build the devices and how historically was made the interaction of light with matters and how we quantified the energy of the light and the matters. But I will continuously, and if you have questions, you can also ask me, and I can return in the end of the class. So as I told, here just a small description of a spectra, and this is the energy related with the spectra. We have some when we have one atom, we have this fingerprint of absorption and emission of the light. So in terms of energy, depending of the number of electrons that has in atom, we can have this fingerprint of the absorption and the emission of the light. So for example, here I have one photon with 18 energy, and the energy to have this electron transition to final state must have the same energy of this transition. So in terms of absorption, and after the absorption, initial and final states, the electron from the final states goes to the initial, and the release amount of photon with energy h me. So if they don't have any electron coupling between the electron and the geometry of the system, the energy of creation will be the same energy of release of this photon. And we can see using some experiment the fingerprint of the atoms through the sharp spectral lines of absorption and emission spectra. So if we have this energy, we have the specific feature of the element that's composed the material. So, for example, we want to investigate how this table is built. We will apply energy on it, and we will see how the energy will be absorbed and how the photon will be released. And this can be described by the transition atomic between the electron of the atom. So, for example, here I just give the quickly here this equation. But in terms of atomic spectra, each lines that you see in atomic spectra will be related to transition between stationary states So when we go to the initial state and final state, both states are stationary, so it will not be time dependent, so it's time dependent. Is time dependent states, and historically the first spectra that was observed was using hydrogen, that is most popular and the easiest atom to observe it. And the hydrogen has one electron, and this energy of the one electron must be here. The transition will be different if we change the frequency of the photon. And there is some series that can be described as this atom spectra. And in terms of energy, Lyman series, Balmer's energy, visible light, Paschen series, infrared light, and further. So after the observation of atomic spectra, together with the photoelectric effect observed by Albert Einstein, everything that was done around these years was supposing that the energy of the material, the energy of photon and the energy of the particles that compose the materials are not continuously described by classical mechanics, but must be described by some theory that are related with discrete energy. So these spectral lights that I said, in terms of if we see, for example, here, absorption, in terms of frequency, to describe this transaction, we must analyze the transaction with a specific frequency, which means that is the frequency for to give energy to the electron go from the initial state to final state here. So when we have this, we call absorption spectra of light. And when we have atomic one material that is composed just by one atom, we will have this sharp absorption. But we know that this just works when we analyze the gas and one molecule. And when we go to, for example, solid state, we must have crystallines, and this interaction, this transaction will be replaced to sharp, not sharp, but broader peak with some distance between the peak correlated to the material's property. So this we will discuss further, but it started with the knowing on the quantum mechanics. And using the hydrogen atom, so the when the light interaction with the electron should give this energy to have this transaction, the electron is not will not more discussed in terms of the particle, but they also must be discussed in terms of light. So it started with Bohr model. So in Bohr model, we have, before Bohr model, we have different models to describe the matter. And the Bohr started to describe the matter as one center of with high mass, and the electron around this center, and the electron goes with orbits, and these orbits are ruled with angular moment of electron. So the electron will be described using this equation in terms the simplest term will be using the quantization of angular moment. So the angular moment of the electron will be described using his mass, and the velocity and the radius that could be quantized using integer number of quantum number, and the constant Planck. And using this equation, correlationship between classical and quantum physics, we could predict some position of the electron here with the radio called Bohr radio, and this is the quantized radio of the electron. So for example, if we have one electron, this would be the distance between the center of the atom and the position of the electron. But this model started with Bohr. It's not the nowadays model, because Bohr just described how the hydrogen works, and it will not work for multi-atoms, for example, because there is some difference in the electron distribution. But in that time, and nowadays, to start to understand the quantum mechanics is nice to mention, but for hydrogen, for example, replacing that constants that I gave the question earlier, we have this quantization of energy for electron in the orbital, and this was the first successful quantum model, and needed to be replaced to be applied in more structures using more electrons and more atoms, and also don't give any perspective in terms of spin, and they basically, the Bohr model is on the semi-classical nature of the movement of the electron. But it's nice to correlate it, and it worked when we see just one electron and one nucleon. Sometimes it I thought that I removed my animation, but I didn't, and I don't know if it is the animation or the maybe Zidane mentioned. So when we described the photon is a wave that can be propagated into the space using wave, and when the photon interacts with matter, it will release the energy through as particle. So and de Broglie in that time thought that if the waves can be particles, why not the particles can be waves? So he used this theory that could be describing any particle as wave. So, for example, we can describe ourselves as wave or somehow particles, and sometimes particles, sometimes wave. And we could correlate our wave, a wavelength, for example, with our interaction with the matter here. But when these dimensions are higher than atomic dimension, the wavelength associated with the movement of the particles will not be important to investigate. So the wave and atomic and the particle relationship will be just important, have important effects when the wavelength of the particle has the same as lattice spacing of the system. So if our wave, for example, has the same distance of the atomic of the wall, for example, it would have some interaction, but we don't have, so it is not we cannot see any effect when we interact with the wall, just as particle, not as wave. So in terms of this, we could correlate the wavelength of the particle through constant of Planck and quantum momentum, and momentum of the particle associated with the observable. And the first experiment to see it, and this experiment is until nowadays used to describe the interaction of the particles with the matter and the duality of particle and waves behavior of the particles. It started with Davison-Garner's experiment, where we have the electron beam here incident on, for example, here nickel crystal, and this beam has wavelength in the order of atomic distance. Here we can see the planes of the material, and when we increase the intensity here, when we give this beam here, it will be scattered, and this scattering will be ruled using the same Bragg diffraction as used by X-ray. So we don't see just diffraction of the patterns of diffraction with photons, but we can also see patterns of diffraction using particles. And this, for example, we can use scanning electron microscopy. We observe the scattering of the electron, and we can also correlate it with the atomic lattices of the composition. And it's nice to mention, but when we work with particles, electrons, for example, we have different interaction because the electron is negative. So, for example, X-ray will go deeper, electrons is more on the surface, but it's also nice because they have both this behavior, but depend of the composition of your particle, you have different interaction with the matter, but they also can be described by Bragg law. Okay, so we started understanding how the classical laws of physics didn't apply in quantum world. And then we see that in the ages of the 90s, 1090, several experiments were performed, and these several experiments performed simultaneously described some as new system that is the modern physics, and this could impact how we can see the materials today, how we can construct the devices. So in terms of quantum world, we also must understand that with quantum, we cannot describe more the observable itself, but we must describe it as probability of the observable be observable. So what means it? That we have some uncertainty on description of some quantity, physical quantities. In terms of position and moment, for example, we cannot measure simultaneously the position and know exactly the momentum of the material that we are, the experiment that we are using to observe. So if we know the position, we don't know exactly the momentum. And if we know the energy, we don't know exactly the time that is observed. So we use expectation values for position, momentum, and energy. So this means that in quantum world, we are not more deterministic. We use statistics to describe the system. And this uncertainty relationship is given by Heisenberg, and the correlation between energy and time and position and momentum will be described using these equations. And as I told, greater precision in position will be uncertainty knowing the moment, and every measurement that you do will be disturbing the system. So you must understand that when you apply one experiment to observe one material, for example, you disturb the condition that the material had. For example, it is usually used the cat Schrödinger, where we can know how how we know that the cat inside the box is dead or alive. We must open the box and see if it's dead or alive. But if you open the box, you will interact with the cat, and this changes the configuration. So the probability will be more described than the exactly of that quantity, physical quantity. So in terms of probabilistic interpretation, we must shift from the deterministic, that is one specific value, but also to distribution of values for that specific observation. For example, here, if we cannot know the position of a particle, we must use a probability to describe this position. So the probability will be given by this equation, where we have the wave function in terms of the position. So the position, the probability will be the density of probability of the density of wave function here. And when we normalize this probability, we can see we must see through the system that we know that the particle is inside this space that we call x plus dx. So, for example, if we have a particle, one electron, we can describe it, this electron, using wave function. In the wave function, that is not a specific value, is one calculation tool. So we use it just to determine how the particle and how the particle are described, but it's not a specific condition. Is not the wave that the particle has, but is the determination of the position that the particle has. And we must use the function in function of position or time. And this wave function will be a function with complex values. And it usually used when you see one observable, you see a probability related to the density of the wave function. And sometimes, okay. So as I told, the wave function, for example, to find one electron in the space in a certain condition of time, and this space is given by one limitation, that the initial condition x and x plus dx. The probability to find will be given by this normalization, and this normalization will fix the amplitude of a wave function. As we discussed earlier, we can associate the momentum of the particle with one wavelength. So the wavelength can be also described in terms of magnitude using the wave vector k, and this will rule the direction of propagation and also rule the correlationship between wavelength and the wave vector. So when we have this system that is described by wave function, and when we want to observe this system, we apply these operators that are the observable of that what you want to observe. For example, you want to observe the position or the momentum, you want to use the operator, the momentum operator, and this will give how the values are expected into the wave function, and it can be described using these operators. And to know the operator, it usually using the de Broglie relationship that I showed on the last slide. And correlating with the waving function, we can see that the waving function here, the action of operator over the wave function can predict the position, the momentum over the wave function. What it can be related in terms of applied quantum mechanics is the so when we apply the potential operator, we can see some aging values that are the observable of this operator over one system. And these aging values P that we called can be described how the operator goes into the system that has some wave function that describe this system. And when we go to 3D, we change the it's not important. We can change the wave function, the operator from 1 dimension to 3 dimension using the gradient. And observable quantum mechanics correspond to operators whose aging values are measurable quantities. So we can measure the operator when we apply on those systems. And we also can go not just for momentum, but also for energy. And when we see the energy operator, we can know how the energy are related with this system when we apply this energy operator. So in terms of energy, as we discussed, the energy cannot be simultaneously predicted using with time. So it's always in terms of time. And when we apply the energy operator, we give the aging values for those operators. And the total energy of the system will be related using the Hamiltonian of the system. For example, here the Hamiltonian for this example, where we have energy cinetic of the energy cinetic of material of a particle using momentum, and the Hamiltonian will have energy cinetic plus energy potential, and when we use this operator, the energy potential does not have operator, just the momentum, and we can use the time dependent solution to describe the Hamiltonian observing this system. When the system is time dependent, we can split the system into a spatial part and time part, and we can resolve the system using just spatial, and using the temporal part here just to describe the evolution of system. So here we usually use it to describe stationary orbitals, for example, and transition, where we don't have any time dependent evolution. So in terms of time-independent system, we have these solutions that could be related to the spatial time, a spatial part, and time part. And the stationary state, in terms of a stationary state, the particles remain semi-energy state indefinitely. So it means that even if the time goes, it will not change it because we don't have any perturbation on the system. This is usually used to describe some transition that is purely stationary, but we know that depending of the material, when we go, for example, from the one initial state to final state, the system changes with the excitation, and then we must also use time-dependent correlationship with the Hamiltonian. So here I just, I lost my, I think during the, but what I just would like to give a brief discussion regarding Dirac formalism. We started using quantum mechanics through Schrödinger equations, but sometimes we don't. It's hard to use every. Just to use the probability itself without using some new mathematical system to describe it. So we usually shift from the probabilities to the dielectric formalism, where we can represent all the system that we discussed using algebra, linear algebra, and these linear algebra are related to the bracket description, and the cat represents a vector in the space, in Hilbert space, and also a cat, cat here represented the vector. And we don't have any specific description, but we can shift the vector without shifting in this description of the system. And also, when we apply those corresponding vectors, which means that is the bra of this agent vector, we can observe how the probability from one state to another state are I forgot the word in English, but how the one state to another state will be overlapped. And this overlap can be described to using these linear vectors. And the measurements usually described using the auto vectors. The operators will give one agent value when it interacts with the system that is this vector. So it usually described the operator using matrix, and the cat and the bra matrix with one vector, that means one column, and one line matrix to cat and bra respectively. And when we apply this matrix in this agent vector, we have these agent values that could be easily understand the measurable of your system. So the Dirac formalism is usually used in quantum mechanics to describe with more the system with more simple ways, and more possibility of the projections. Okay, so just an overview on quantum mechanics. What matters for devices physics is the relationship with the particles and the potential. What means that how we can see how is the energy of the particle when they have no potential, or limited potential, or infinite potential. And this we can fine-tune the device's layers in terms of this design. So in terms of electron in one system that has no potential, so it means that the electron goes freely into the space, and the potential energy this 0 in terms of position because it's constant. So it means that we don't have any difference on force during the position of the electron. So we have the electron freely moving into the space. And when we have this condition, and we want to solve the Hamiltonian of the system and see the eigenvalues of this Hamiltonian, we can see that the energy that is given by this equation are correlated with the energy of operator Hamiltonian over wave function, and then applying, resolving this waving function using the exponential part because of the solution of this equation. So when we do derivative twice, we must use some exponential description. So the solution of this wave function will give aging values of this, and these eigenvalues are independent of the position of the particle in the system. So it means that the energy is independent of the position. And when we know exactly the energy in terms of the uncertainty description, we know that the energy here in terms of position is parabolic. So we don't see here the graphic, but if we do a graphic here with free and electron with free energy, free potential. So the energy will be described using a parabolic system. And we know in every position exactly the energy of this particle. So in this way, we don't have a quantization of energy. It means that in the case of free electron, the electron is not, the energy of electron is not quantized. And when we don't have this quantification of the energy, we cannot apply the uncertainty principle, and the energy will not, so the energy will be null independently of the time, and the momentum also will be null independent of the position. When we use the here is just a break into the wave packets. When we see a particle moving into the system, we can describe the position and the wave function of these packets as wave packets. So here is the wave packets of the system. And using the Fourier transform, we can describe the movement of these wave packets as one specific value distribution, actually, with this Fourier transform. So even that is the free electron that has no the energy is not described by quantum point of view, but when we have the propagation of electron, this electron can be propagated using wave packets. In terms of in case where we have the potential wall, we have some limits where the electron can move. So here we can see that the electron can go inside this wall from 0 to L, and the potential wall will be infinite in these boundaries, and we can describe the movement, the moment, and the energy of this electron when we use it, for example, when we want to see some specific moment, for example, we will have some specific values depending of the position and the so it will have some discrete description of this momentum and energy inside this box. So to solve this equation, we must use the potential that is 0 when the electron goes from 0 to L, and is infinite when the electron goes lower or higher than L and 0. So to solve this, the wave function can be solved using this equation, and their energy, aging values of the energy, will be used in terms of quantum number. So it will appear here the quantum number. That means that we have specific values of energy in terms of the position of electron inside the box. So here applying as depending of the frequency of electron, we have this difference. Looks like one. I forgot the word in English, but corda. I don't know. It's not the same as French, the corda. But it will look like one. I forgot the wording. But it will be like the finite of this corda. Someone knows corda English? Maybe my students.
Or
Uh,
the rope?
no, the cordon.
It's not a rope.
No, not the rope.
Okay.
Let me see.
How do you say in Brazilian? Order?
See.
Like this? Oh, okay. Okay. Is that this?
It's how we can do. How we can do it in English.
It's called. Now the rope. Yes.
It's one string. String.
String. Okay.
It's a string. So it can be like this string with this potential. Oh, I didn't know that I could. I draw it here. I didn't know actually
How did you?
how I did
Maybe
it.
yes.
Not
With the
here.
red one. And
No,
okay.
no, it's not.
It's a mystery.
Yes, I didn't know how it appears. I can see it in the video. So if we have this, it's like the string in the, and when we shift the frequency of the vibration, we can have this specific energy that is correlated to the electron inside this potential barrier, and the electron can have just discrete eigenvalues. So it means that the electron has just 1, 2, 3, or 4 in terms of the quantum number, which is correlated to the energy 1, 2, 3, 4, and further. And this is just analyzed stationary states, and the probability density is resolved using time-dependent theory. Okay, I think
It stays on.
Oh, I didn't write it. I didn't use it.
Right. Big guys. You see?
Yeah, it's not.
See that?
No, it's not a problem.
Okay.
We can just finish in the quick. I don't know. My mind. So in this case, we have this. When we have a limitation in the proposal described. So infinite system. So we have some specific values of position and energy of the electron. And when we shift this potential to a finite potential, it means that we have this barrier of energy, even that is the same distance of the barrier. And here we have a no unknown value. For example, 1 here is infinite. So it means that the electron can go inside the barrier, and depending of the width of this barrier, we can have some expected position and energy inside the barrier. So is the energy potential 0, and here the potential is our one specific energy. So in terms of the devices, we can use materials to confine the electron inside this box, or to allow some specific values inside this width. So we use it. We can describe this finite potential using quantum tunneling. And the wave function decrease exponential with the position inside the barrier. So if the barrier is thick or big here, the width of the barrier, so the wave function will be decreased and will disappear. And if the width of barrier is sharp, for example, maybe depending of the particle that you are analyzing here, if it's electron or if a hole, you can block this movement inside the material. So here is more beauty, the sketch. So here we have the wave function in energy. In terms of energy, here we don't have any potential applied. Here we have a barrier with a high potential applied and one width with here the barrier starts with 0, position 0, it goes to position A, that we can see further that is correlated with a crystal lattice. So here we have this reduction of wave function inside the barrier, and after it will be reduced, the wave function is modified because of the perturbation of the barrier. So we can describe this system also. And when we use it in the materials, we can analyze it in terms of the crystal lattice and also in terms of different material systems. So in terms of correlationship of this finite potential and the crystal lattice, It means that when we have this potential correlated with the parameter of the crystal, we have the crystal being the electron be disturbed due to crystal orientation or the atoms that compose this crystal, and we can correlate it with this system described, this model described by Chronic Penny, where we can associate the position of the crystal lattice with the interaction of the electron inside electrical potential barrier. So it means that when we have the distance between the atoms, it will have some barrier that will prohibit the transition of the electron here, and we can go to another seat here just with energy sufficient to overcome this potential barrier that depend of the atom composition, depend of the material composition, depend of the electron position in the orbit also. So this is the basis for the block states. So the block theorem means that we have the wave function described just inside the box that are defined by the crystal lattice, and the propagation of the wave function is described by the exponential, and the direction of the propagation will be affected by the crystal lattice, where we can correlate it using the position of the electron inside this crystal lattice. So in terms, for example, here, one solution in terms of the wave vector, no? Is that in some specific points of the lattice, we have some forbidden bond where we must overcome it with a specific energy that is directly related to the transition between the allowed states and forbidden states. So to overcome these two states, for example, we must insert energy in the particle that has a higher energy than this barrier here to overcome this forbidden energy band. So this forbidden energy band is usually described as gap for inorganic materials, and depending of the energy of this barrier, we can say that the material has metal or semiconductor or insulator properties, and this density of states that are the distribution of allowed energies inside the box can be described depending of the crystal lattice of the material. Here we don't give any perspective on the spin, just in terms of the crystal lattices and the electron distribution. But when we go with the spin, that means that the energy depends off of the time also. We have just different distribution inside the density of states. So the energy band will be used to describe the levels of the energy allowed to the particles, to the electron inside the material. We have some regions that has energy allowed and energy forbidden. And these regions that came from the crystal lattices of the material, we can use it knowing the crystal structure of the material that you are observing. And we use this system to describe and to construct the interfaces that are mandatory for the device operation. So in the next Tuesday, we'll discuss on how the energy band can be used to build the materials properties, and how we can join two materials with different properties to have one specific behavior into the junction. So for now, it's I must check it. Why is the translation is not so. Okay, I think it's solved. Have questions on the topic?